হ্যালো, তাহলে আমরা আমাদের আরেকটা ভিডিওতে এসে পড়েছি। এখন ধরো তোমায় একটা লোহা দেওয়া হলো, এটা আয়রন বিম, ঠিক আছে? তো সেটাকে আমি প্রাথমিকভাবে অল্প হিটে, মানে অল্প টেম্পারেচারে হিট করলাম, ঠিক আছে? মানে টেম্পারেচারটা অল্প বাড়ালাম, কি চেঞ্জেস দেখবে বলতে পারো কি? আরো বাড়ালাম, আদৌ কি চেঞ্জ হবে কিচ্ছু? মানে কোনো কালার টালার চেঞ্জ হবে, কিছু হবে? হবে। রেড হট আয়রন আমরা পড়েছি এগুলা, এবার একটা টাইমে হোয়াইটিশ হয়ে যাবে, এরপরে ব্ল্যাক বডি। এভাবে আমরা বুঝতে পারছি যে এই যে কালার, ইট ইজ ডিপেন্ডেন্ট আপন টেম্পারেচার। তাহলে কি কালার মানে কি? ফ্রিকোয়েন্সি হয়, নইলে ওয়েভলেংথ। তাহলে ফ্রিকোয়েন্সি আর ওয়েভলেংথের সাথে টেম্পারেচারের কি ডিপেন্ডেন্স, সেটা দেখার জন্য আমরা কি করব? চলো, আমি আর বেশি বোঝাবার আমি হয়তো এখন পারছি না, আমরা একটু অভিজিতের কাছে যাই। সো ওভার টু ইউ, অভিজিৎ।
So good morning, good afternoon, good night everyone. So whoever is watching the video, this is to all that today from Juvenile Gurukul, myself Abhijit Shaw, I'm going to start a lecture on the blackbody radiation. So on the completion of 3 years of Juvenile Gurukul, this topic was selected by my friend Devanujan Nath. So as his friend, myself, I'm going to deliver a lecture on this topic today. So let's proceed. So the emergence of the blackbody radiation. Now the thing is what this blackbody actually is and how this theory actually came into study. The theory of blackbody radiation emerged in the late 19th century as a result of attempt to understand the behavior of electromagnetic radiation. Now you all know what electromagnetic radiation actually is. It's actually an electric and a magnetic field oscillating in a perpendicular phase. So this is how the electromagnetic wave actually propagates. We all know about that. Now, for studying this electromagnetic radiation more precisely, the scientists they devised a new term known as the blackbody radiation. So what this blackbody radiation actually is, we are going to see in the next slides. Okay, so this blackbody consisted of a this black consists of a cavity. If this is the blackbody, it consists of a small cavity. Now, what is this cavity and why this cavity was required to study on this? I'll discuss in the coming slides. Okay. Now, the phenomenon of blackbody radiation refers to the emission and absorption of electromagnetic radiation by a perfect absorber and emitter of radiation, which is known as the blackbody. Actually, this blackbody is an ideal thing in physics. It can absorb the radiation completely and it can emit the radiation completely. So it's an ideal blackbody who can absorb all and it can radiate all. Okay, in day-to-day cases, this is not the case. Okay, so in the mid of 1800s, experimental observations has revealed that the intensity and spectrum of radiation emitted by heated objects depend on their temperature. Okay, uh, we know that suppose this is a rod, this is a metallic rod. Okay, this is a metallic rod. When you start heating the rod, the rod's temperature starts to rise slowly. It's not that at an instant the temperature rises. Okay. Now that we know that heat is a form of energy. If the rod is at low temperature, that means what? The energy of the rod's body is lower as compared to the rod's body when it is completely heated. So what scientists found that the more the temperature of the rod is rising, the energy the rod is emitting is really high. It's in the case of the rod, it's not in the case of the black body. Okay, so the black body is somewhat similar to the case we found in a metallic rod. The rise in temperature, the change in color of the rod. So I will discuss all these things later. That how when the temperature rises, it actually depends on the energy of the system. The wave theory of light is something very different, and in the coming slides you can also see that the existing theories on the wave theory of light just failed to explain this blackbody radiation observations. Okay, now let's go to the next slide. The concept of blackbody. Now, to understand the concept of blackbody, I'm going to show that how this blackbody actually looks and how it actually works. Okay, so I'm drawing a blackbody. This is a cavity. My drawing is not that good, but I'm trying to explain the thing. Okay, this is a black body. Now, in the last slide, I gave you the example of a metallic rod. Okay, that is when the temperature of the rod is rising, that means what, it is absorbing much more heat from the system which where the rod is inserted. Now, this black body, this ideal black body was actually consisted of metallic balls. These walls were made of metal. Okay, metallic walls. Okay, and inside the black body, the inside portions inside the black body, the the walls are completely dark. The walls were completely dark. Not only not only that, the black body was made in such a way, if any light with some incident radiation enters, it cannot come out. Okay, so the walls were working like a absorber that was absorbing every source of light that was coming towards it. Like a sponge, when you put it in some water, the sponge absorbs the water, and the water places gets dry out because the sponge has absorbed all the water from there. In the same way, this black body was also absorbing everything what was coming inside it. Okay, so the black body was colored black. The color was black, dark, intense black. You know the lamp black. It was intense black. It was 99% black. It was near 99% black. Okay, so I showed you the hole. Now let us imagine a ray of light is coming inside the black hole. Let us consider that this ray consisting of energy E, some amount of energy E, and this energy is dependent on the frequency of the light as well as the total number of photons there, because the number of photons are more, the more the energy the light is carrying. Okay, so the light is having uh, some quantized form of energy, and this light, when strikes inside the black hole, 96% of the total energy 96% of the total energy is absorbed by the wall. Like when the wall is like this, when the light is falling, like this is the total energy E, and 96% is absorbed, means only 4%. This absorbs 96% of the radiation. This is the total energy which is falling on the black body wall. And this black body wall is absorbing 96% of the radiation. 96%. Okay. And the rest 4% is only exiting. This 4%, like this 4%, when falls on the second surface, it again absorbs the 96% of this 4%, and at last nothing lives. This ray completely vanishes inside. It is completely absorbed by the walls of the black body. The thing is that I want to tell is not the entire thing is working as black body. Okay, not the entire thing is working as black body, because whatever is going through this small hole. Okay, so this hole is actually working as the black body, not the entire thing. The thing is colored black, that is fine, but not the entire system is working as black body, but this small hole. this small hole is only working as a black body, because whatever ray is going inside, it is not able to come outside ever and ever again. For for infinite time, this ray is vanished. It will never come back. This is a actual and ideal black body. It will absorb everything which will go inside. And now you may just ask the question that you may ask a question, what will happen, if the light falls 90-degree inside this hole? So we all know that if it is going 90-degree, it will just strike back in the same angle. Actually, to avoid that, to avoid that thing, there is a small triangular notch inside. This avoids this light to strike backwards if it comes at an angle of 90 degree to the surface. Okay. Now let's proceed to some more things. So this black body, as I showed in the previous page, this black body this is the black body. Okay, now this is heated. Now I am applying heat, like I told in the first slide. The metallic rod was heated. The temperature was rising and it was emitting some radiation. Now the thing will be used here. Now when I'm applying the heat, the temperature on the walls of the black body rising. The temperature is rising. If I make a graph, this is the temperature and this is the time, then it is increasing. The temperature inside the black body is increasing after time, because I'm applying heat, constant heat, and this heat is accelerating. The heat is accelerating. This heat is accelerating the energy of the walls of the black body. Like the heat was the heat was increasing the energy of the walls of the black body. Okay. So now if the walls of the black body are heated, okay, they will start emitting radiation. They will start emitting radiation. Okay. Now, when it starts emitting radiation, something very beautiful happens. We all know how radiation is formed. Okay. We all know that how radiation is actually formed, is generated, how it's generated. Okay. So when there is an accelerated charged particle, accelerated charged particle, when there is an accelerated charged particle, it means inside an atom, the charge is oscillating at a very high energy, because you are applying heat to it. When the atom neighboring to this one atom is heated, every single atom on the walls of this black body, atoms on the wall of the black body, every single atom on the walls of this black body is excited to a very high energy level. Okay, it's excited. Okay, it just goes from one energy level to another energy level, because it is thermally excited. Now this accelerated charge particle formed due to the accelerated heat energy provided to it. The accelerated heat energy provided to it, the accelerated charge particle starts emitting radiation, and a form of radiation that carries energy, because this accelerated charge particle is the only reason that can give rise to energy, and this electromagnetic energy just starts flowing inside the black body. And after some finite time, when the energy has reached some maximum value, at temperature T starts emitting, the black body starts emitting those radiations, the walls and the walls and the cavity, which was having charged particles, they they start emitting radiation. Now, this is a very interesting phenomenon. How is this actually happening? People for many years they tried to study that how the things actually work. No, because when you are rising the temperature, that the walls of the black body they are getting heated up, and that leads to the energizing of charged particles on the walls to emit radiation, because they are moving from one energy level to the other energy level, and for that they starts emitting the radiation. Now, the experimental observations. Experimental observation. The radiation that was coming outside from the black body, the radiation that was coming outside from the black body was having some finite energy distribution. Okay. Now we know that the energy of a radiation is dependent on the frequency, of the wave that is radiating. Okay, the frequency of the wave is radiating. If I tell that this is the black body, no matter what's the chemical composition of the black body was, it was solely dependent. It was solely dependent on the temperature of the black body, not the chemical composition. The the chemical composition is completely out of this term of this black body radiation. No matter what is chemical composition is used to construct this black body, the thing is only going to depend on the temperature. Okay, because more the temperature is, the more the energy is, and we know E equals to H nu. So that you can say nu is proportional to E. More the energy will be rising, the frequency of the radiation will be increasing. Okay, so that's a different thing. Okay, I'm going to draw a graph that will show you the spectral energy density and the frequency of the black body radiation. This is the y-axis and this is the x-axis. What I have actually drawn is this y-axis is the spectral energy density, and this is the frequency. Okay, so what the spectral energy density actually means. So the spectral energy density is actually the energy emitted per unit area, per unit surface area for a fixed interval of frequency. So this is actually the spectral energy density, and it's very low for low values of frequency, and increases as rapidly as the frequency increases. Now, this energy density is actually what I've just told, that it's the energy per unit area per unit time. Okay, and it's solely dependent on the frequency of the radiation coming outside of the black body. Okay, now if the radiation is coming out in low frequency, that means what? That means what? If it is low, suppose it's in this part, if it is low, then what? The spectral energy density will be also low, na? For example, For example, if if I have a white paper, if I have a white paper, okay, and I have a syringe, or the injections we just use to give vaccines or kind of things to people. Okay, now for example, there is a complete white sheet like this. There is a complete white sheet like this. Now, if I take a very thin needle and I start pressing the injection, then the fluid which will come out at a high pressure, it will be just spreading on the few portion of this page because the needle is very thin. So per unit area of that needle, suppose what I am telling that there is a needle, okay, and here is a paper. So if the needle surface, the cross section area is very small, then whatever the thing will be coming out from here, it will touch very small part of the paper because it is very thin. It's very thin. So the density of the fluid coming out from the surface density of the fluid coming out is actually very low. Okay, because per unit area it is coming very low. Per unit time, per unit area it is coming very low because if the fluid is coming less, if the volume of fluid coming coming less, then how the paper will be colored in a dark way? No, no, the paper will be brighter, but there will be some few spots, low, low, bright spots because very few amount of color is just coming out from the needle now. In the same way, the the spectral range density and the frequency is related in the same way. Okay, almost. I'm not telling that it's completely the same thing. I just want to demonstrate some day-to-day physical phenomena that are related with this. Okay, now what will happen? What will happen if I just increase the size of this nozzle? Now more amount of fluid will come inside, more amount of fluid will come, and as more of the volume of fluid is come, so it will make a bright, much concise, a much concise shape of color on this paper. This is much concised. So much concised and it will be much like contrastic. It will be much contrastic. Okay. So in the same way, the way I have increased the flow of the fluid by increasing the size of this one, in the same way, increase the if I increase the frequency, then per unit area, per unit time, we will get much more energy density. Do you understand? Have you understood that? The more I'm going to increase the frequency, the more the energy is going to be increased, and more the spectral energy density will be increasing up to some limit. And there, next, something very interesting comes. Okay, now there is a very beautiful thing. You can see now up to this place, up to this level, as I'm increasing the frequency, the spectral energy density is also increasing. Up to this part, everything is working in a classical way. The thing is increasing. As we're increasing the frequency, the spectral energy density is increasing. But, just see this thing. See this thing. It is decreasing. It is decreasing. And somewhere it will tend to zero. At a very large interval in the x-axis, like in the frequency range, if you increase the frequency to a very high range, then at some point in future it will touch the zero axis. So what was actually happening? What was actually happening was like very much disturbing. Okay, it was very much disturbing what was happening because we know if we are increasing the frequency, the energy density is increasing in a very drastic way, but after certain range of frequency, it's decreasing. Okay, It means what? Decrease the energy density decreases and further increase of frequency. Energy density decreases with further decrease, further with further increase in frequency nu. Energy density decreases with further increase in nu, and nu is what? Nu is the frequency. Okay, so mathematically it was becoming very hard to describe that what was actually having here. Actually, what was the thing actually happening? Because you are increasing the temperature, energy is rising, the energy inside the black body is rising. Okay, but the incident, the radiation was just coming out, the spectral energy, the radiation that was coming out, that was somehow showing this one. Inside the black body, rising the temperature, the energy is increasing, but in the but from the whole of the black but from in the whole of the black body, the radiation is coming outside. It is showing this kind of is showing this kind of phenomena, which was like really very much uh, uneven, and it was like very much confusing for the phases of that time. Now, the actual thing which was happening, I'm going to discuss that in a very small and descriptive way, because there are some large derivations. Okay, so let's proceed. Let's see what is the main theory behind the observation which is saw, that when you're increasing the frequency, when increasing the frequency, the spectral energy density must have increased, but no, it has decreased after this limit. Okay. Now, in the next slide, I'll just say something on the spectral energy density and the quantized energy that is coming out from the cavity itself. So, I'm drawing the graph once more. Okay. Now, this black body is kept at a constant temperature T. This black body is kept at a constant temperature T, and now the radiation is coming out from the walls. And according to the Planck's quantum hypothesis, it was assumed that this radiation was having quantized energy E equals to NH. Okay, so the N is the quantum number and H is the energy of the radiation consisted by each single photon, that is H. Okay. Now here is the energy. I'm taking E lambda, and this is the wavelength. Okay, so this is the thing we obtained at the constant temperature of the black body, and this was the this was the graph, and the area under this graph was the energy density. Okay, like like the way, uh, if I take a small portion of this lambda, that is d lambda, okay, and this was the graph. So and the function of and the fun and this is the value of the function. Okay, that the y-axis is the value of E lambda. This is the D lambda. So E lambda, D lambda, it is the energy coming out. E lambda, D lambda is the energy that is coming out of this black body. Okay. Now, in this case, the temperature is fixed. Okay, in this case, the temperature is fixed. In this case, the temperature is fixed. Let us consider this as T1. Temperature equals to T1. At temperature T1, it is emitting this radiation. Now, what is E lambda D lambda? I'm telling in a brief that E lambda D lambda, it is equals to the amount of energy coming out, amount of energy coming out within the range lambda to lambda plus D lambda. Like I told that there is a very small range. Okay, it is lambda plus D lambda. I understand from, if I zoom this part, I zoom it, then you can see that this is lambda and lambda plus D lambda. So energy between this range, this means what? If I just pulling out the range to just height of E lambda, then this area is E lambda D lambda, because the difference is D lambda. If I have a rectangle of length E lambda and I have a breadth of D lambda, then the total area will be what? E lambda D lambda, E lambda D lambda. So this was the energy it was coming out from the black body. In this sense, we applied the temperature T1 at a constant rate. Okay. It was at temperature T1. The peak was at temperature T1. Here is my E lambda and there is my lambda. This was at temperature T1. Okay. I'm suddenly rising the temperature to T2, from T1 to T2. What you think? What will happen if I have something, some sort of object which is metallic, and if I increase the temperature from T1 to T2, what will happen? The color of that object will try to max out in a way that the color of the thing will change. If there's a very red hot iron, and if you're hitting it to a very high temperature, the color of that red hot will come to bluish and white. Okay, because if there is I think you have seen this, if there's a rod and if you hit this, at first it comes to red, and then what? And then and then the color just goes to like bluish white, goes like bluish white. Okay, because the energy density at red was something different, and at bluish white it's something different. It comes to a like a blue color kind of gradient. Okay, so we're not going to discuss this here, because we just need only this thing. uh, After we are rising the temperature T2, the energy is increasing. Okay, T2 is is proposing is proportional. T2 is proportional to the energy, or you can say, more the temperature T2 is rising, the energy is also rising. Okay, the energy of the radiation is rising. If the energy of the radiation is rising, we know what equals to H equals to Hc by lambda. If E proportional to nu, then E proportional to 1 by lambda, right? E proportional to 1 by lambda. So this E proportional to 1 by lambda, you imagine if I increase this, what will happen? This. Then we can say that if T is increasing, that means what? E is also increasing. If E is increasing, that means what? This lambda is decreasing. So what we will expect that if T1 is lesser than T2 or T2 is greater than T1, then the peak of T2 will appear somewhere here. The peak will appear somewhere here. Okay, because see, now this is the new lambda 2, this was the lambda 1. The peak at temperature T1 is obtained at lambda 1 and the peak at temperature T2 is obtained at lambda 2. Okay. So what I have just shown that if the temperature was rising, the energy was also, that means what, lambda was decreasing. And this was the proof that the lambda has decreased because the energy was high, the temperature was high. If I can write that E2 is higher than E1, so that implies what, lambda 2 will be lesser than lambda 1. Okay, so this was another observation. Okay, now For, for each particular temperature, the black body is emitting the maximum radiation at this wavelengths. At this particular wavelengths, the black body is radiating the maximum energy. Okay. Now, from here we will come to something called the Wien's displacement law. We'll come to something called the Wind displacement law. There is a derivation for this Wien's displacement law, but before that I just want to say the Wien's displacement law in a very brief manner. Wien's displacement law. The Wien's displacement law. When we are rising the temperature of the black body, we're obtaining some kind of lambda for that temperature. Like at that wavelength, the black body is emitting the maximum radiation. So we'll mark it with lambda m, or the peak value. The peak value will mark it with lambda m. Mark it with lambda m. Okay. And the temperature was like T2 or some different temperature was there. So according to Wien's displacement law, the maximum radiation at the wavelength where it is occurring multiplied with the temperature of that particular scenario is equals to a constant. Okay, like lambda t and t equals to constant. Like in the previous case when we are obtaining the lambda 2 which was lesser than lambda 1, in the case that T2 was greater than T1, in this case this lambda 2 was giving the maximum radiation. So lambda 2 came to lambda m, and this T2, lambda m T2 equals to lambda m, it should be 2, lambda m1 T1. Okay. This is the Wien's displacement law. Lambda m2 T2 equals to lambda m1 T1. Can you see one thing very beautiful? Here, one thing which is there is very wonderful. That is, if temperature is increasing, this lambda m2 is decreasing. And so the quantity here, this is high, this is low. Okay, and this is low, this is high. That means what? The balance is maintained. You are multiplying two things and the balance is maintained. Like what? If I multiply one quantity 3 with another quantity 4, it will equals to 2 into 6. Something is very high, something is low. Something is very high, something is low. You're just manipulating two things on the different side and you are balancing. This thing is balanced naturally. There's nothing the scientists have did something from a different point of view from physics. It was happening naturally. This is a phenomena which scientists were trying to explain. This was very wonderful. Like you are multiplying these two things, the previous case and then the another case, and you're getting the same result. And this equals to a constant. Okay, this equals to a constant. And the value of this and the value of the constant and the value of the constant is 2.89 into 10 to the power minus 3 meter Kelvin. The SI unit here it is meter because lambda is in meter and K temperature is in Kelvin. So we know the conversion that 0 degrees Celsius equals to 73 Kelvin, 273 degree Kelvin, and this lambda. And generally, in maximum cases, the lambda comes out to be nanometer range, that is 10 to the power minus 9 meter range. Okay, so this is the constant. Okay, so this is one thing. Next, we will see the area under the graph. The area under the graph. This was the graph. Okay, this was the graph. This is the E lambda, and here is the D lambda. Okay. Now, as I told that, what is the energy density in the range of E lambda to T lambda? Okay. So this is D lambda, and this is A lambda at some temperature finite temperature equals to T1. Okay. Now, mathematically, it was derived that this energy was in the order of the fourth power of the temperature. Yes, the energy was in the order of the fourth power of the temperature. That was very interesting. And this equation was later it was derived to E equals to sigma T to the power 6 to the power 4. And it's a Stephen Boltzmann constant, which is 5.67 10 to the power minus 8 meter watt meter square temperature to the minus 4. As I have told you that the radiation which is coming out, this is the radiation which is coming out from the black body. It was consisting of the quantized energy E equals to nh nu. Okay, so inside a black body, there is not only one wave that is just coming out. There's not one wave. There are millions, there are billions, there are trillions. Because the surface is compiled of trillions of atoms, and there are trillions of atoms. Okay, there are quintillions of atoms, there are quintillions of electrons. They are oscillating, they are at a very excited state, and they are emitting huge number of waves, electromagnetic waves. And they are of course formed by the accelerated charged particles. I've told earlier. Okay, so how you can describe the total energy density that was coming out, the energy flux that was coming out from this cavity? Cavity was emitting good amount of radiation. Now, how can tell about the energy density in the total form of like the total number of waves that are coming out? So how you can describe that? So a formula was coined. That was Actually, it was not coined. Actually, it came with some calculations. You know that how the Planck constant was like found by the help of the back calculation from the graph of the Blackbody radiations. So I'm just going to write the formula in a very simple way. That is E nu d nu, it equals to c by 4. It's a constant. C by 4 n nu d nu. Okay, and the next part is h nu by e to the power h nu by kt minus 1. Okay, so what is the meaning of this entire thing? What is the meaning of this entire thing? Nu is the frequency at which the charged particles are oscillating. Charged particles are oscillating. E nu d nu is the energy density in the range nu to nu plus d. Now we are considering the case of nu to d nu because if energy is needs to be increased, then nu also increase. We are considering the case of d nu because it will be simpler. So this energy density E nu d nu can be represented how? Okay, let me give you a good example. Okay, suppose you have a toy car. Okay, you have a toy car, and somehow that toy car is something very different. That toy car has the option of 4 batteries, 6 batteries, and total of 8 batteries. Okay, you can run the car by 4 battery also, 6 battery also, and 8 battery also. Now, if you give 4 battery, the car will run. The car will surely run, but at a slow rate. If you give 6 batteries, it will be much higher. And if you give 8 batteries, it will just twice, not twice, but almost twice as fast as the scenario when there was 4 batteries. Because you are adding extra weight with the batteries, and the car is speeding up, but there is a deceleration rate due to the weight of the batteries. That's something different. But when you are increasing the energy source, you are getting a much better output. Blackbody was written as E nu d nu. Okay, this is the energy density in the range nu 2 nu plus d nu per unit volume. Okay, this E nu d nu can be written as E nu d nu equals to c by 4 n nu d nu h nu by e to the power h nu by kt minus 1. Now, in this formula, there are three very important terms. First of all, this constant c by 4. There is a very beautiful mathematics behind how c by 4 came. Okay, this c by 4 term is actually a lot to this energy formula. This nu d nu is also a result of rigorous mathematics. This nu d nu can be calculated by understanding the total number of standing waves. Now, what are the standing waves? These standing waves are the soul of the energy distribution of the EM waves. The standing waves are actually those EM waves that are carrying the energy. Okay, there are total number of standing waves in the order of n nu d. Actually, this is the total number of standing waves. Okay, in the black body. Okay, if you have a battery of some energy E, and if you are having 20 batteries, then the total energy the battery can supply when current it will be 20 into E. So like that, this energy density per unit volume can be calculated as the factors of this 3 by 4 is total number of standing waves and the total energy associated with each standing wave, or the average energy, not total. It will be better if you say that average energy associated with the standing wave. Okay, so in each standing wave, then the average energy will be h nu by e to the power h nu by kt minus 1. Okay, this is the average energy, and from the this came from the Planck's hypothesis. When Planck tried to correct the graph that was uh, having some uh, that was having some problems with matching with the experimental data. So Planck, at that time, Planck derived this term. So in the next slide, I will show that how this term was actually derived. Okay, now this nu d nu has a value. This this nu d nu has a value. Okay, and this nu d nu has a very important role in understanding how the energy is distributed. Okay, like I can show you, like this is the black body. I'm showing cubical wave. It's not that beautiful at all, but for the sake of understanding, the standing wave should be enough. So there are the standing waves. They are between the walls. So they are between the walls of the black body. So they are carrying the energy, okay, in the order of c by 4 into some average energy per wave, standing wave, okay, into the total number of standing waves. Okay, this nu can be written as like 8 pi nu square by c cube into t nu. Okay, or the nu is actually 8 pi nu square by c cube. Okay, so this is the value for the total number of standing waves in the frequency nu inside the black body. Now, one better name you can give this to a standing wave is that a harmonic oscillator. This is standing wave is from a harmonic oscillator, or because the accelerated charge particle is oscillating, it is emitting radiation. So you can say that this standing wave is a result of the energy that is coming from the harmonic oscillator. So you can see this nu as the total number of oscillators rather than just standing waves. You can tell in a much precise way is the number of oscillators. Number of oscillators oscillating in the frequency range nu to nu plus d. Okay, so this is the total number of oscillator. Now as I have told that the average energy per standing wave, you can better modify it to write like the average energy associated with each such oscillator that is carrying the electromagnetic wave, that is giving rise to the energy, the oscillator, the oscillation of the charge particle, the oscillation of the charge particle is leading to the electromagnetic wave. Okay, the oscillation of charge particle are leading to the formation of electromagnetic waves, and these oscillating charge particles are giving out some energy, some average energy, and that average energy can be written in the way h nu by to the power h nu by kt minus 1. So in the next coming slide, we can show that how it's coming, that how the how the average energy of each oscillator is h nu by 2 by h nu by kt minus 1. Okay. Now, the average energy associated with each such oscillator, oscillator is h nu by to the power h nu by kt minus 1, and this came from where? Max Planck hypothesis. Max Planck hypothesis. And the temperature is kept fixed at temperature equals to T. At this temperature these things actually happen. Okay. Now what is at what conclusion we have arrived at? E nu d nu total energy can be given as the total energy density for a unit volume can be given as C by 4 8 pi nu square by C cube h nu by to the power h nu by kt minus 1 d nu. Okay, so this is the total energy we obtained. Okay, now I'm going to derive the average energy part. Now before deriving the average energy part, I want to tell one thing, a very important thing that changed the way how quantum physics was started. People started understanding the behavior of light, radiation, but from this particular path the things got very different. I'm showing you how. When I draw the graph, when I draw the graph of the average energy distribution, okay, the E lambda or the E nu, E lambda, D lambda, sorry, the E lambda and the lambda, okay, and there's a temperature T. So this graph was from experimental point of view. This graph was experimental, okay. Now, what is the thing just happening here? I told like when the temperature was increasing, the energy density was also increasing. But here something very different was happening. Now, few scientists came up with some explanations. One of them was Rayleigh Jeans. Rayleigh Jeans quantum mathematical situation where 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 he explained the first part of this graph up to this one. Okay, Rayleigh Jeans theoretical graph was used like this. Okay, this was Rayleigh Jeans criteria. Okay, this was his approach. I'm going to show you how he made this approach, and this approach was wrong because Rayleigh Jeans tried to understand how this thing was happening, and he coined some terms. But when the values of the different terms in the equation was put, the theoretical graph came out to be just like this, but it was not the actual graph. Rayleigh Jeans graph was not the graph we obtained by experiment. His graph was theoretical, and that is not matching with the graph we obtained from the experiment. Okay, so Rayleigh Jeans failed in explaining the behavior of this graph. What Rayleigh Jeans proposed didn't match with the experimental graph. This was theoretical, and this was based on Rayleigh Jeans distribution, and this was theoretical, and this was the experimental, and this is one of the biggest failures in explaining some physical phenomena, and this was later termed to be the ultraviolet catastrophe. This was later termed as the ultraviolet catastrophe. Why? Why it is ultraviolet catastrophe? Because because if I make the graph for nu and mu, then this was the experimental one. Rayleigh-Jean's graph only satisfied for lower frequencies. Rayleigh-Jean's graph only satisfied for lower frequencies. But for higher frequencies, Rayleigh-Jean's law failed. Rayleigh-Jean's graph just failed to explain the thing when it went to higher frequencies at very high temperatures. Because when temperature was increasing, the frequency, the energy of the wave was also increasing. But Rayleigh-Jean's just failed to explain that. That's why it was known as ultraviolet. Ultraviolet means that the 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 region of the light white has very high energy. Okay, the ultraviolet part, the spectrum from in the spectrum of the deep pure spectrum, the ultraviolet part is towards this one, and this is very high energy, and at very high energy means at very high frequency, Rayleigh-Jean's graph failed because Rayleigh-Jean's graph was increasing up to the lower frequencies. It matched somehow up to lower frequencies. Okay, but after that it didn't match. This is known as the ultraviolet catastrophe. Now, now this ultraviolet catastrophe has some few things. Okay, we seen in the previous slide that the the number of oscillators was 8 pi nu square by CQ. This is the n nu. Okay, so by Planck's hypothesis, which we are going to show just after a few minutes, the Planck hypothesis, we came that this one was from the Planck hypothesis. But before that, Rayleigh-Jean's law just described from the classical thermodynamics that the total energy associated with each harmonic oscillator was that half kt plus half kt, and that is equals to kt. Okay, that was from the classical thermodynamics. Okay, that inside a black body, from the total nodes of vibration, we get the total energy to be half kt plus half kt equals to kt. This was from Rayleigh-Jean's. So I am not going to show that how it is coming or how this term was coming because that takes time. So I'm just telling you that this term was actually before kt. Like Rayleigh-Jean's criteria was having the term kt here, not this part, but Rayleigh's criteria was having the term kt here. Means for him the expression was like this, that 8 pi nu square by CQ, okay, 8 pi nu square CQ into kt T nu. This was the energy density. This was energy density which was just coined by Rayleigh-Jean's, and this didn't match the experimental graph, and this went like this, and this went like this. Okay, this went like this. Sorry, my diagram is not that good. It just went like this. Just went like this, and it never came towards the lowering part. That means what? For higher frequencies didn't work out. For higher frequencies it didn't work out. So what could have been done to match the graph? Okay, so match the graph. Actually this graph now, this part was from, this was from classical thermodynamics. There are a lot of things in classical thermodynamics which we have generally studied in the gas systems and all that kind of things. This classical thermodynamics works. Okay, and here also Rayleigh-Jean's implied that particular thing. Okay, that from the kinetic and potential energy of the waves we get this kt part, and this is a total energy, but that didn't work out. Okay, then came Max Planck. How Max Planck's Max Planck's correction. Now we're going to derive the the average energy part. Okay. So according to Max Planck, he told that energy when carried by photons, they are discrete, and they are in the form NhE, where n is the quantum number and h is the energy carried by each such photons. Okay, in the blackbody radiation, when the atoms are excited, the charge the, the charged particles are excited to such an extent that they accelerate and they starts emitting the EM waves. Okay, and according to Max Planck's hypothesis, this EM radiation was consisting of some discrete and some continuous fractions. The discrete the discrete energy was turned in the way like in NH nu, and the radiation which was coming out, that was continuous. Okay, I'm not going to the mathematical form because that's a little bit complicated, but I'm just telling in a brief that what Planck suggested was that the energy which is coming out from the black body was continuous, and the energy which is coming, which was releasing by the oscillators, was discrete. And we know the discrete energy just relates with the quantas, or the small packets of energies. They are just coming out in small packets of energies. Okay, but in Einstein's photoelectric effect, what Einstein suggested was that the radiation was discontinuous. Now photoelectric effect is a very different thing than what we have done here, but in some future lectures we will be going very deep into the things, that how these conclusions of discreteness or discontinuousness or continuousness was. Now how we can derive the average energy density which was given by Max Planck. Okay, now let us consider at first that there are few energy levels. Okay, this at n equals to 0, the ground state, n equals to 1, n equals to 2, n equals to 3. Okay, and these are the energy levels E3, E1, E2, E1, 0. Okay, and there are, suppose, the number of oscillators that are oscillating can be given as in the n0 ground state n0, in the first state n1, this state n2, and this state n3. Now this can be also written in this way, that nn also written in the way that nn equals to n naught e to the power minus en by kt. Okay, so this is how the number of oscillators can be coined. Okay, the number of oscillators oscillating in some energy range like E1, E2, E3. Okay, and to find the average energy, you can do what? The total energy. Find average energy. What is energy? Average energy can be written like total energy by number of oscillators. Okay, this is the way we write the total energy, right? Now what you can do, that is, this is the symbol for the average energy. You can write like summation n equals to 0 to infinity. The total energy of all the system consisting of the oscillators divided by the total number of oscillators is to 0 n equals to n equals to 0 to infinite nn. Okay, now we're just and we know what en equals to nh and nn equals to n naught to the power minus nh nu by kt. nh nu by kt. Okay, now let's proceed the derivation. And so here you can write like this, that the 0 into h nu for e0 plus 1 into h nu e to the power minus 1 into h nu by kt, okay, plus 2 into h nu e to the power minus 2 minus 2 h nu by kt, 2 h nu by kt, plus, and like the same way we get that because en equals to nh nu, for n equals to 0, nh nu equals to 0, so this is the 0 part, it will be 0, it will be 0. So now the total number of oscillators you can write like, since nn equals to n naught to the power minus nh nu by kt, for n equals to 0, it comes to n naught to the power 0 equals to it will be just this part, for n naught equals 0, it will just come to 1. This will come to just n naught. Okay, this come to just n naught. Since here we are having the n naught term, we are having the n naught term, we are having the n naught term, and here also we are having the n naught term, n naught plus n naught e to the power minus h nu by kt, then n naught e to the power minus 2h nu by kt. Okay, because this one and come to n naught, and this n naught, if we take common, if we take this n naught common, like here if we write the n naught common e, sorry, n naught, if we just write that h nu to the power minus h nu by kt plus 2h nu to the power minus 2h nu by kt plus 3h nu, have to go like this, and divide by n naught to the power minus h nu by kt plus, there was one n naught, plus pi to the power minus 2h nu by kt, and this thing like this go on. So n will cancel, and you will get h nu to the power minus h nu by kt plus 2h nu to the power minus 2h nu by kt plus, like go, and here we get this n naught will come to 1 because we can gonna take common as 1, so 2 1 plus to the power minus h nu kt plus to the power minus 2h nu by kt. Okay, now we can take h nu common, and you can write h nu to the power minus h nu by kt plus 2 to the power minus h nu 2h nu by kt plus 3 to the power minus 3h nu by kt. Okay, and we can write 1 plus to the power minus h nu by kt plus e to the power minus 2 h nu by kt. So we are getting a similar kind of condition in the above and the lower part, the numerator and denominator part. Okay, and this will get like this and this, and here you can take one thing common, because minus h nu by kt, right, minus h nu by kt, and you can take the thing common. Take the thing common, 1 plus 2 to the power minus h nu by kt plus 3 to the power minus 2h nu by kt, and like just the way 1 plus to the power minus h nu by kt plus to the power minus 2h nu by kt, and go like this. And you can consider this thing e to the power minus h nu by kt, this thing. Let us consider e to the power minus h nu by kt equals to x. Okay, we'll use this in the next term. h nu equals to h nu into x 1 plus 2x 1 plus 2x plus 3x square and plus, and below you can give 1 plus x square plus x cube plus, yes, and then we can write like h nu x 1 minus x square 1 minus x whole power minus 2, it's the binomial expansion, and 1 minus x or minus 1. And I think you know one thing, that 1 plus x whole to the power n equals to 1 plus nx plus n into n minus 1 x square by 2 factorial. Okay, this thing is the formula we use for the expansions, and the average energy can be now written as equals to h nu x 1 minus xs minus 2 by 1 minus x whole to the power minus 1, and h nu x by 1 minus x will give you like h nu by 1 by x minus 1, or dividing x on both sides, you get this. Okay, so this will lead to h nu by this x was taken as what it took x, we took x equals to the power minus h nu by kt, right? We took this, so this will come to 1 by x, means 1 by x will be equal to the power h nu by kt, because the minus term will vanish since we are making it reciprocal, so it will be to the power h nu by kt and here minus 1. So this was the average energy formula. This was the average energy formula we obtained, that is h nu by to the power h nu by kt minus 1, and this led to the matching of the graph with experimental values, like for higher frequencies. Now Planck's graph was matching some Planck's. This one was near the this one was the observed experimental, and this one was the Rayleigh jeans. By this way Planck solved the problem, and now for Rayleigh jeans the formula was like the energy density formula was like 8 pi mu square by c cube into what kt, but kt into like d nu for the range d nu, and for Planck, I'm just showing the terms that are affiliated with each of the condition for Planck. For Max Planck, it was just like only c by 4 n nu d nu, and now this n nu d nu term was like, before is the only n nu d nu n nu term. So this one just came like h nu by to the power h nu by kt minus 1. So you can see the big difference, that is this formula here comes out to be 8 pi nu square by cq, the total number of oscillators oscillating in the range nu to nu plus d nu, and so that's total thing d nu. Okay, it's the a nu d nu. You can do like this. Sorry for that. Like this, and for here it was just like pi nu square cq kt, and that was the difference between the two formulas. This is how the problem of ultraviolet catastrophe was solved. So thank you. And so the things that are required to be discussed, and in some later videos in future, I'll just go deep into the things like how the number of oscillators was calculated. That's a very rigorous calculation. That's why I didn't perform it here. But here, the things I've showed, uh, these are actually easy things, because and see, so very simple things.